Is it orange over there? All right, well, welcome to yet another graduate seminar. This time we have Zachary Dorson talking about
Carlitz Polynomials.
So he lied.
A little bit.
A little bit.
Say why. That's the wrong. Okay, so the reason I lied is because it says in the title and in the abstract something about the Carlitz exponential. But as I was, working out the kinks, I realized it takes too long to develop that stuff. I think I don't have time to do both of them at the same time. So we're just going to be focusing on the Carlitz polynomials. But I think there's enough cool stuff there that hopefully it'll still be interesting. So I think the general point is that I can go like all the way there? Okay. So I think the most interesting thing in this talk is to start, we know that cyclotomic extension, so if you take the rationals and you extend by some root of unity, e to the 2 pi I over k, that these are nice extensions. It's very easy to describe, like their Galois group and stuff. So we like these kinds of extensions. And what we're going to develop in this talk is a similar theory, but for this field instead, Fp parentheses t. So we want to somehow find similar extensions of this that behave in that way. And we'll do that through Carlitz polynomials. So I'll just start by defining the Carlitz polynomials. We're going to do this with a sort of recursive definition. So let's start, I guess, Carlitz polynomials. So we'll denote, if we have some m in Fp bracket t, the Carlitz polynomial associated to m we will denote by bracket m of x. And this will be in Fp t, oops. This will be a polynomial in both t and x. And the way that we're going to construct these is by starting out by saying if we have 1, if our m happens to be 1, we'll define that to just be x. If it happens to just be this, just t, we will define that to just be x to the p plus tx. And then probably the most important one is, this allows us to extend it, is if we have this, we're going to say that this is this one, but evaluated at e to the n minus 1 of x. So now we know how to construct it. If we have these things and extend it in the obvious way with linearity, right? If our m, which it's in here, so it's going to be some ci, oops, not x, t to the I, then we will say this is equal to this sum just extended by linearity, like that. And this gives us a way to construct this for any m that we start with. So I think the first thing to do maybe is to compute a small example, and that'll give us maybe a clue of some of the nice properties. So since it gets a little bad if you do something too big, I'll just start with t squared. Here is probably fine. So we'll try to compute an example. We want to find out what is this. This is the Carlitz polynomial associated to t squared. So the first rule that I should probably number these also, so they're easier to, so we'll say 1, 2, 3. So the first thing is we'd probably like to use this, right, to reduce it, because we know how to deal with t, but we have to get to t. So this is going to be equal to just t, and then evaluated at 2 minus 1 is 1, so that. And now we know what this is just by the second rule. That's going to be x to the p plus tx. And then, I guess I have to go a little lower. And then we just evaluate this, but at here, sort of. So we're plugging in this for the x's. So we're going to get x to the p plus tx to the p plus t times x to the p plus tx.
The m symbol on the inside is it's a polynomial or the variable t?
Yes.
Okay.
And then we're ending up with one that'll have t's and x's in it.
And then these rules will be recursively defined bracket.
Yes. Mm-hmm. Yeah. And then, I don't want to write that, I'll go over here. So we will just, first off, we're in characteristic p, so we're just going to raise both of these to the p power. So we get x to the p squared plus t to the p x to the p plus, and then I'll distribute the other side because we want to write it as a polynomial in x. That's nice. So we'll get, t x to the p plus t squared x. And just grouping things, we get x to the p squared plus, let's write the coefficient first, t to the p plus t squared x. And this is going to be, that's our final answer. It's a polynomial in x with coefficients in here. So there are a few things that one might notice about this. One is that we only have powers of, our indices are powers of p, which is pretty specific. Another thing is that the degree 1 coefficient is what we started with, right? We wanted to find a thing for t squared, and we ended up with that degree 1 coefficient being t squared. And neither of these things are coincidences. We can say about the first one, I think the first important fact about these that I'll say as a proposition is that, well, I probably want to define something first. So first, we should define if f is just some polynomial in there, f in here is a p polynomial, we just want it to be of the form cix to the, I wrote t, I should use the same variable. We want it to only have powers of p in the indices. And the first proposition, obviously, is that if we have this m in here, we say mx is a p polynomial. And I think the proof is pretty routine. It's a little just computing things kind of, so I don't think if it just, we just want the powers to be, no problem. So, and I should have written the, I goes from 0 to n, so will be degree p to the n. And so about these you can notice that it won't have a constant term, right, because p to the 0 is just 1. So, I think I will omit this proof because it's not that important, I don't think. But it does give us a lot of properties. I think it's very important. It's important enough to include. So, let's see. The first thing to notice is that, well, I should write proof of 4. So the first thing to notice is this property is telling us that it would be sufficient for us to prove it for t to the n here, because right, we'll just be adding everything up in this way. It'll just be a sum of things like this. It'll be, t to the n minus 1, etc. So it's sufficient to just prove that t to the n times m is, t to the n evaluated there. So that's what I'll do. And we will proceed by induction. So first off, the base case, we just want to show that t times m of x is equal to t evaluated at m. And this we can just compute. So if we know that m is a polynomial, right? It's some sum ci t to the I goes from 1 to n. And right, we can pull the t inside the sum to get t to the I plus 1 of x. Now we have our third rule over there, the sort of recursive one that allows us to write this as t evaluated at t to the I plus 1 minus 1 is just I of x. And then this linearity lets us pull the sums sort of inside. And what we want to do is write this as m again. So we have the sum on the outside, and we have both of those properties, 1 and right there, 1 and 3. We just want to write this as, there shouldn't be a thing here. Whoops, there shouldn't have been a thing there. We pulled the sum all the way to the outside. And rearrange this, and now we're pulling the sum back into the inside. So we're getting t evaluated at this sum ci t to the I. Where's t to the I? I should keep writing the indices. Equals 1 to n. Equals 0 to n, sorry. And yeah, that's fine. Okay, and then we recognize this as m. So this will just be t evaluated at m of x, which is what we wanted for the base case. So now the next step is to, use our inductive hypothesis. So we will assume it's true for t to the n minus 1 and show that that means it's true for t. So it's a similar sort of computation. We will start, I guess I'll say, all right, whatever. I will say, now we have t to the n times m of x, and do the same thing here where we write it as a sum. I'm going to omit the indices this time. I think we all know what they are. And we pull the t inside. So this becomes this sum t to the I plus n of x. And then, again, we use linearity to get the sum on the outside. ci t to the I plus n of x. Now, I'm going to go up there. Now, we just use this recursive thing again to write it as ci t evaluated at t to the I plus n minus 1 of x. And then we're going to again pull the sum into there. So we're going to say this is equal to t evaluated at this sum ci t to the I plus n minus 1 of x. But in here, this is just going to be m times t to the n minus 1. So this is evaluated at, well, I should write it first, t to the n minus 1 times m of x. And then, right, this is our inductive hypothesis. So we get t evaluated at t to the n minus 1, evaluated at m of x. And then we have that third thing over there, the recursion t evaluated at that of something is just t to the n plus 1. So we end up with t to the n of m of x. And that completes the proof. So that's a nice property. We'll be using that a lot later. Okay. What else can we say? Another thing, another pattern, and I won't prove this, but I will just note that, right, earlier I said, what's up here? Earlier I mentioned that it wasn't a coincidence that we have t squared x as this degree 1 term. So that's something that will always happen. I guess I can write it. I should write it down, shouldn't I? So I can just write another corollary. So we have m of x as degree p to the m and the coefficient of the degree 1 term, I guess I should say, the degree 1 term is m. So that's nice. We'll see in just a second why we need this. But I won't prove it because, again, it's a little, I don't think it helps very much. So one immediate thing we can see from that is that the x derivative of this polynomial will just be m. So, and that will end up meaning that it's separable. So I will say, should I write it as a corollary still? It'll be a proposition. Okay, so proposition. And x is separable. And the proof for this is, for it to be separable, we want it to be coprime with its, and I should say it's separable as a polynomial over fp bracket t in particular. So I guess like with respect to x, maybe in some sense, and that is important. Or no, I'm sorry, not bracket, parentheses. So I should write that, shouldn't I? So of course we'll end up with a polynomial in here, but everything in here, you know, we can just think of it as a polynomial over the field of rational functions instead of the ring. So we'll say, when we view it like that, when we say this is an fp parentheses t bracket x is separable. And the proof is the x derivative of mx is m, which is a unit in that field, of course, in fp parentheses t. So this, right, is an element of, hello, this is an element of that, no, sorry, of this. The field of rational functions is the field of quotients of this. So it's necessarily a unit. It's like how you do it. So that gives us that it's separable because it has to be, coprime to it. So that's nice. That'll of course tell us something about when we start talking about extensions later. That'll be a nice fact. Or maybe not even later, maybe right now. Yeah, okay, so now we want to start talking about extensions of that field of rational functions. So should I maybe erase that? Can I go there, or is it kind of... Okay, well, I don't know if maybe you'll get people in the shot. Doesn't matter. I don't want to make everyone move. There's really no... Yeah, I think I don't want... It's kind of, I don't want the people... Yeah, I'll erase... This one maybe isn't as important. Yeah, who cares? Okay. So we will just go back over here. I guess I could use this whole one too while I'm at it. So now we want to look at field, I should say algebraic extensions. Algebraic extensions of that field of rational functions. K over Fp parentheses T. There's a broom there. Yeah. So, yeah. Okay, so if we have an extension of this, we know that, what this means is that we can view this as a vector space over that. So we have that the extension is a vector space over the base field. And if it's a vector space over this field, then it's also a module over that field, right, sort of trivially. And that means we can view it as a module over, so if we have this, then we can view K as an Fp bracket T module. So, and in a sort of trivial way, by just multiplication. Because, this lives in there. It's a restriction of scalars kind of thing. But there's a more interesting structure that we can put on K, and that is through those Carlitz polynomials. So we want to define view with, I guess, an obvious way. Yeah. This way. You also have I'll call it a Carlitz action, which I will define in a second. So if we have some m in here, we can let it act on an element of K by m times alpha is just going to be this Carlitz polynomial evaluated at alpha. And it's nice that I still have this right next to it. So you can sort of see that these are essentially exactly what we need for this module action to be like a real action, right? We need that it respects the addition in K, which is what this is saying. We need that it respects the addition in the ring, which is what this is saying. And then we need that it has that associativity property where it, respects the multiplication in the ring. So these three properties, I guess I'll write them over here. So 1 over there gives us that m acting on alpha plus beta is equal to m acting on alpha plus m acting on beta. Then 3 gives us that m plus n acting on alpha is m, oh, I don't need that, sorry, m acting on alpha plus m acting on beta. And 4 gives us that m times n acting on alpha is m acting on n acting on alpha. And so that's just to give you an idea of how this just falls out of that over there. So this is nice. It's a different module structure, and it'll be sort of what gives us the rest of the neat stuff that we talk about. Hopefully. Let's see. Yeah. So we just took K to be some extension, right? In particular, we're going to be very interested in the action on the algebraic closure of this. So I guess I'll go over here. This. We are interested in the Carlitz action on f, p, t bar. So this is where we'll find a lot of the interesting stuff. And we'll call this, just to differentiate, because you always also have that trivial action, just to differentiate, we'll call this the Carlitz module to make explicit that we're talking about this with this module structure, the new one given by the Carlitz polynomials, not the trivial one given by multiplication. So this is cool. Okay, I see. So now to start with that, I haven't talked about any sort of roots of unity or cyclotomic extensions, but I'll start doing that now. So one way you can describe the roots of unity is, let's say we think about the z action on q bar, so the multiplicative group of the algebraic closure of Q. If we look at this and we want to know what are the points in here where acting on it by something in Z gives us the identity, which in this case is 1, right? We're asking for the set of, call them, I don't know, alpha in Q bar such that M acting on alpha, which since we're talking about the action on the multiplicative group, that's going to be exponentiation instead of just, or it'll be multiplication, which will, be exponentiation, right? Equals alpha to the M equals 1 for some M. And you can see, right, this is exactly the roots of unity. And these are, right, the torsion points of this, in the sense that torsion is used for modules. So we want to develop a similar thing for this right here. We want to look at torsion points and see how those act. And those will end up being the analogs to the roots of unity. But I'll just make a definition here. So let's say, so how much time do I have? Definition. If we start with some M in here, the M torsion of well, I should say the Carlitz module, of the Carlitz module is this set let's denote it by lambda m, is the set of all, well, I should start using lambda maybe. Lambda in here such that m evaluated at alpha, oh, I said lambda. Lambda is equal to 0. So this is, it's kind of like the annihilator, right? But instead of fixing something in the module, we're fixing a scalar. And we're asking, what does m annihilate in here? Which also, given the action that we've defined, corresponds exactly to what are the roots of this polynomial when we evaluate it, as a polynomial in x, what are the roots of it? And
You want lambda in that?
oh yeah, sorry, I do want that. Yeah. So of course, yeah, we're interested in that. Okay, I think I should not do it. Okay, so the first thing to note is the size of this. We can sort of just, we know what the size is because this is algebraically closed. We know the degree of this, and we're looking for all the roots of this. So we know how many roots that has in here. So just a note is that for lambda m, the size of that is just p to the degree m, like, I don't know, this is it over there, yeah. From that little proposition, we know the degree of m, so this is going to give us the size. So that's nice to know. And we can say a little bit more about this. So something that comes from the fact that it has that additivity, it's an additive polynomial. That gives us that this is a subgroup of the additive group. It's closed under addition, right? Because if we have, let's see, lambda m is an additive subgroup. I won't go through everything in too much detail, but right, if we have two roots, we add them together and we evaluate the polynomial with them, we can split them up. It'll be 0 plus 0, that'll be 0. It's a similar argument. We just get it from the thing that was right here before I erased it. So that's nice, right? And that's similar to what we have for roots of unity. They're also subgroups, but multiplicative still. But we can say a little bit more about them. Particularly, we can say that they form a submodule. So that requires a tiny bit more. Just get rid of this too. So yeah, I'll say, I don't know, theorem, why not? M is an F P T submodule. And in particular, again, we're talking about that action, a submodule of that. Yeah. Okay. And the proof of this is not too bad, so we'll do it. Let's see. Yeah, so this is where we need that products and compositions thing. So what we're asking to show this, we are just going to, hopefully I convinced you that it's an additive subgroup. So now all we need to do is show that it's closed under scalar multiplication. So showing that is saying, right, if we have some lambda in here and some thing in here, it being closed under scalar multiplication is saying that if we act on this by n, we want this to be in, sorry, there was supposed to be an m there. So we have a lambda in lambda m. We want this to stay in lambda m. And what does it mean to be in lambda m? It means that it's annihilated by m. So what we're asking is this 0? And we know that we can turn this into a multiplication because of the corollary at the start. So this is just going to be m times n acting on lambda, and then multiplication is commutative, right? So we'll end up with n acting on m of lambda, and this is 0 just by hypothesis. It's given that it's 0. So this will be n of 0, oops, equal sign there, and then that will be 0 because this is a p polynomial, so it doesn't have any constant term. So this shows that it's closed under scalar multiplication, which is nice. It's a submodule with that nice action. Yeah, okay. So now we are going to look at the generators of this, because we can say a bit about those. I didn't really use that space. Yeah, so now we want to find what are the generators of this. And I'm going to just sort of do it. It's you know, just a discussion thing. It's not going to be super. I'll hand wave some details, but hopefully I'll convince you about it. Let's see. So to start, this is definitely finite, right? We found its size there. And it's definitely torsion, just by definition. It's elements that are annihilated by this. So everything in here has some polynomial that annihilates it. You know, at least m does, but there might be other things. And that means that if we have, so let's see, I'll just say generators of lambda m. So if we have some lambda in lambda m, we can look at the annihilator in, right, we just want the annihilator of this, right, is going to be all of the elements in this, all the scalars of pt, such that if you evaluate them there, that equals 0. So, right, this is the usual definition of annihilator. See how that one was sort of opposite. And that's nice. That gives us, that'll allow us to find the generators. So the first thing to note is that this is an ideal in here. Annihilators form ideals. And this is a principal ideal domain, Fp bracket T. So that means we have a generator of this ideal, a single one. And if we take it to be monic, then that's unique. So we know we can write that it is equal to that for some n. And next, we also know that if we look at every element in here, there will be a finite amount of these. So we can pick the one, and also, there's something I was supposed to mention. So this, we call this n the Fp T order of lambda. And I'm going to call it order because it's going to act like sort of the order of a group element. I'm going to appeal to some group theory things in the rest of this. Yeah, I think, let me see how. Yeah, so the first thing from group theory is if we have definitely sure works in just abelian groups. Maybe there's more cases where it works, but if we just have two group elements, we can always find another one whose order is the least common multiple of their orders. I guess you could say, so if we have, that's a thing from group theory. I don't think proving it will help. Should I write it? Yeah, so let's say we have lambda 1 has order, n. Lambda 2 has order m. Then there exists a lambda 3 with order LCM of n and m. So this is just a fact that I'm going to state. It's sort of what you might hope would happen because this works in groups, abelian groups. And what this tells us is that if we pick this n to have maximal degree, then it has to have everything else has to divide it. So if we say let lambda 0 be such that its FP has maximal degree. Right. Then from this property, we have that everything else has to divide it, right? Because if there was something that didn't divide it, then if there was something that didn't divide it, right, then their product, the LCM, would have to be in there, but that contradicts the maximality of this degree. So that's nice. So we can say that then, and so from that, we can conclude that order, sorry, I should have named it. We're going to call that n. So lambda 0 will be an element in this lambda m such that its FPT order has maximal degree of n. Then we can conclude that n of lambda equals 0 for lambda in lambda n. And why is this the case? Because we know that whatever this thing's order is, it divides n. So we can write n as a product, and then we can use that composition thing to get that. So now we have this element with maximal order, in a sense. And we want to show that this generates things. Let's see. So another thing that we can say about n is something about its degree, right? Because we know that n has at least as many zeros as are in this thing. So we can say, I guess I'll go over here now. So that means we can say that the degree of n is greater than or equal to p to the degree of n, which was the degree of n, right? Because it has at least that many zeros. And from that, what do I have to do? Okay, so another group theory fact that I sort of have to appeal to is we have that the order of every element in a group divides the order of the group. And we have a similar fact here where all of these things divide sort of the order of the group, the order of the module is m, sort of by definition. So we know that this divides m, which, sorry, that's just something that I'll state because I don't think I have time to go through that. So another fact is that this n divides m. And from these two facts, we get that n is, and we also assume that it was monic at some point. So n is a scalar multiple of m. In particular, it's the monic scalar multiple of m. So that gives us that the ideal generated by n is the same as the ideal generated by m, which will be useful. Okay, now we want to look at more of this lambda 0 that we picked. So we have 5 minutes. Okay, this might be the last things I can do, actually. Sure. Okay, so now we want to look at this lambda 0. So we picked it such that this has maximal degree and this thing works. And now let's look at the set of, well, I shouldn't say, the set of, we just want to evaluate it at a bunch of different polynomials and see what we get, such that we just start with a b and fp t like that. And we're going to argue that this has the same size as this, and thus they're the same. So that's going to be the point here, is that this generates lambda m as a fpt module. And the way that we're going to argue that, I should just bring this over here. Okay, so one thing to note is we can always write whatever b we're taking. Yeah, definitely less. We can always write this b, we can divide it by m because we're in a, did I write it anywhere? We're in this, the field of rational functions is our constants in this polynomial ring. So that means it's a field, right? So we have Euclidean algorithm. So we can write this as some q times m plus a remainder r, and r will have degree strictly less than m. So that gives us, if we evaluate that, that's just going to be qm, I'll skip the linearity step. Plus that. This is definitely 0, right? Because we have an m there, and that was how we, that was where we started, was with m annihilating all of these things. So this is just going to be r of lambda 0. And what we can conclude from that is these things only depend on the equivalence class of b mod m. So that gives us, so the size, I should have maybe given a name to this, whatever. So the size of, I will give it a name. We'll just call it lambda without anything. We want that this is equal to lambda m. So the size of that is going to be the size of fp, I guess we want x mod the ideal generated by m, right? And this is just going to have size from, field theory. This is just going to have size p to the degree m. And that is the size of this. And since this is a submodule, right, it's closed under this operation of evaluating it at B. So that gives us that, so you can write, these are the same. So this is generated by this lambda 0, which is what we would want to be able to find a generator similar to how we can find a generator for the groups of the roots of unity. So yeah, I think now I'm out of time. Yeah, so.
So you spent some time defining this M torsion set.
Yes.
You proved that it was a group. You proved that it was a submodule.
Mm-hmm.
So what else does it do?
What else does it do? It essentially acts like the group of roots of unity. In yeah, so there were some other things that I wasn't able to get to that support that analogy. We can say other things like.
So when you construct your analog of cyclotomic extensions, you're adjoining these elements.
Yes, that's what I would have
I see.
liked to get to. Yeah, exactly. And these elements are going to act like those groups of roots of unity in a few ways, right? If we have that M is co-prime to N, then plus N is going to be isomorphic to Mn, right? So this is familiar from just, Zn, well, it doesn't matter, right? Zm, and this is an isomorphism as an FPT module. So we still have that modular structure. Of course, this is the same as that. This is just one of the analogies. There are plenty, but you get a lot of statements like this that are essentially the same as from the cyclotomic
Do you know
theory.
what Carlitz was trying to do with these extensions?
I don't know in particular. I know that he did start from a sort of different way. He started with the exponential, actually. He defined this, this formal power series, and he came across these polynomials. Essentially, one of the things there is you can describe these sets in terms of those, in terms of that exponential. In a similar way, right, we can describe the roots of unity in terms of the normal exponential. We can describe these sets in terms of the new exponential. I honestly don't know his exact motive, though.
What is it? You can see cyclotomic extensions. They can be easily connected to like balance.
Yeah, I mean, honestly, I don't know if this particular stuff, I don't think this particular stuff is current. This is like definitely pretty old, like mid 1900s. That's true. That's what, but then I mean, that didn't work out, so I'm not sure if I don't know if people are currently studying this particular thing. I know that Carlitz modules are a special case of like more general theory that is still being studied, the Drinfeld module stuff. But
This connects to Drinfeld modules eventually.
I mean, the Carlitz module is a special case of one, and yeah, so it's but it's maybe a nice case to study because it's sort of the simplest possible instance of that object. So in that sense, it's maybe nice to study.
Just to make sure that we check this. So this is in general, it's just any field of characteristic, or do you use like FP for all these definitions?
For all of these definitions, I was doing it with FP. That's actually a good question. I don't know that any of this stuff would break if you did just a field of characteristic P. I think most of it just depends on that.
The algebraic theory will remain the same. The thing that changes is when you pass to the various compression.
Okay, sure.
Like that.
And maybe that would come in when you're talking about the exponential. That's when you have to start using the completions, probably.
Because if you switch to instead of FP of T, you want to use a global field you want to use a field of characteristic P, you can also develop a similar theory that at a certain point you will have a theorem to prove that it's to be.